Hello everyone. In this video, we will talk about the NMRS, which is the Nuclear Magnetic Resonance Spectroscopy. We will discuss about the principle and analyze the 13C and 1H NMRS and provide some example problems. So first, we will talk about the principle of the NMR. We should know about the magnetic property of the nucleons. First, there are two types of nucleons, protons and neutrons. Protons have charge E, and its rotation produces some spin, and this will create some magnetic moments. I will call it as mu p. And neutrons, although it doesn't have charge, but it is composed of many quarks. Quark had charge, and its rotation also produces some magnetic moment. And these magnetic moments will combine to create the neutron magnetic moment. I will call it as mu-n. So now we know that both proton and neutron have their magnetic moment. So let's see the influence of the magnetic field on the magnetic moment. So let me draw the magnetic field B0, the magnetic moment mu, and the angle B theta. So the potential energy is minus mu b, there's a dot product, so it's minus mu b cosine theta. The equilibrium position is corresponding with the equation, and there's two values, 0 and pi. So the 0 angle corresponds with the energy minus mu b, and the pi angle corresponds to the energy mu b. So we can see that the parallel orientation corresponds to the lower energy, which is known as the alpha spin state. And the antiparallel position will correspond to the higher energy known as the beta spin state. So let's see the case of one proton and the applied magnetic field B0 like this. So there will be two states, alpha and beta state. The proton is in alpha state, but if we illuminate some light with appropriate frequency, we can push this proton into the higher state. This state is less favorable and is beta state. So what is the appropriate frequency here? So although we have two values here, 0 and pi, but it cannot be like exactly parallel or anti-parallel with the applied magnetic field here. So actually it presets with the frequency f0 is equal to 2 pi gamma b0. Here gamma is just the constant of proportionality between the angular momentum and the magnetic moment. So when we see on the absorption spectrum, it will appear like a peak like this. But not all nucleus can be used for NMRs. For example, if we have the even number of protons and neutrons, all the spin will be paired up and cancelled out, so it cannot be used for NMR. For other cases, it can be used for NMR. But we know that the nuclei are not alone. They are surrounded by something called electron, and that will create the electronic environment surrounding the nucleus. So electron has negative charge, and the movement of electron will create some magnetic field, and actually that magnetic field will be anti-parallel to the original applied field, B0. So the effective magnetic field will be B0 minus BE. So the electron actually reduces the effective magnetic field, so it also lowers the difference between the energy level between two states, alpha and beta state. So here if we draw, this is the intensity axis and this is the energy axis. So the original peak will move here due to the reduction of the energy difference. So this is called upfield, and this is called downfield. This effect is called shielding effect. And the nucleus here with many electrons around it is called shielded. And the nucleus alone is called de-shielded. Yeah, shielded and de-shielded.
Let's talk about carbon-13 NMR. It's possible to count the number of carbon atoms by using carbon-13 NMR. The basic factor that determines carbon's chemical shift is electronegativity of neighboring atoms. An example would be the carbon-oxygen double bond. Since oxygen is more electronegative, it will attract the electron clouds towards them, thus shielding carbon atoms and allowing magnetic field to be higher. This causes it to resonate at a lower field at around 160 to 220 delta. Next, let's talk about the structure, which has an interesting carbon-13 NMR spectrum. As you can see, there are 8 carbon atoms in the structure, but only 6 peaks are observed. This is due to the symmetry of the molecule. The carbon atom 4 has the same and has similar environment with carbon atom 4'. And this pattern is also obvious on carbon atom 5 and 5'. So carbon atoms 4 and 4' only correspond to one peak, and the same goes with carbon atoms 5 and 5'. In addition, carbon-13 NMR is really useful because we can determine the environment of each carbon atom. For example, in an experiment, if we have two possible products, like the diagram shown, we can actually use the NMR spectrum to determine which is the right product. And in this case, it is the one on the left.
So in HNMR we have similar case, so we can divide chemical shift of hydrogen atom according to its neighbors, as you can see here. So let's see some examples. Yes, so in this molecule you can see that these blue atoms have different environment compared to these green atoms. That's why in the spectrum they will give 2 peaks. And you can see that there is a symmetry line here. That's why these atoms are same as these atoms and they will give just 1 peak. Alright, and in this example you can see that actually these 2 atoms give 2 different peaks in the spectrum, and the reason lies in the stereochemistry of this carbon atom. So if we draw it, you can see that it has 4 functional groups, and hydrogen atoms have different orientation in the space. That's why they will give only 1 peak in the spectrum. And in fact, if you draw a symmetry line here, you can see that these 2 atoms actually are similar. That's why they will give only 1 peak. Same is with these green atoms, they will give another peak, and these 6 atoms will give another peak. In the third case, however, you can see that these 2 atoms are in the different orientation in the space also. That's why they will give 2 peaks in the spectrum. But you cannot draw a symmetry line here, because here the hydrogen atom is replaced with OH group. That's why it will give even more peaks in the spectrum. Another thing that we can get from NMR is not only the existence of different kinds of hydrogen atoms in the molecule, but also their relative number. So how can we get it? You can see from spectroscopy that this peak is much higher than this red peak, and it corresponds to the hydrogen atoms here, and we can get it by integration of this peak. It means getting area under this peak and compare it with the area under this peak. So let's denote it as A1 and divide it to the A2, which comes from here, and you can see that it equals to 3. That means that number of red atoms is 3 times less than number of green atoms, which is exactly what we expected to get. So another phenomena which we can observe from HNMR is spin-spin splitting, which is splitting of one peak into several peaks, as you can see here, which can be explained by N+1 rule. We call it N+1 rule, and it states that the number of multiplets in the single peak equals the number of neighboring atoms plus 1. So in this case, these red atoms have 3 neighbors plus 1 equal 4. That means it will have 4 peaks, while these blue atoms have only 2 neighbors, so 2 plus 1 equals 3, which corresponds to these 3 peaks, which we call also as triplet. So let's see where this N+1 rule comes from. So splitting of one peak occurs because of the neighboring atoms, which have their own magnetic field. And as you know, it can be either parallel or anti-parallel to the applied magnetic field. So parallel will shift it to the left, and anti-parallel will shift it to the right, as we already know. And because we have 2 hydrogen atoms, we have 4 different arrangements of them, and you can see that these 2 will cancel each other. That's why they won't shift the original peak, and it will stay the same. And because there are 2 of them, intensity will be higher here. So you can see that CH3 peak will split into the 3 because of the 2 neighboring atoms. So you can calculate the number of peaks by using the Pascal triangle. So let's draw it here. So in case of the 3 neighboring atoms, we will have 4 peaks with relative intensity 1, 3, 3, 1, which you can see from red graph.
Here is another example to apply the knowledge that we've learned to a real problem. Given the composition of one compound, and you would like to know its structure while using NMR spectrum, you are given the following data. You have 2 peaks, which correspond to 2 types of hydrogen atoms, and you can see from N+1 rule that this one is split into 3, which means it has 2 atoms nearby. Whereas here, it has 5 peaks, which means it has 4 atoms nearby. We can guess that this 2 means that these hydrogen atoms have a CH2 group nearby, while these hydrogen atoms may have 2 CH2 groups nearby. So from this, we can predict that we have a chain of CH2 groups. And this H2 corresponds to this peak because it has 4 neighboring hydrogen atoms. And this 2 corresponds to this peak because it only has 2 hydrogen atoms nearby. And you can also see that this peak is actually on the left side, meaning that it has some electronegative atoms nearby. Probably bromine atoms are attached to them. While here, it's more on the right hand side. That means it doesn't have electronegative atoms nearby, and its formula exactly matches what we had in the beginning. So this is the answer.